So let's go ahead and do another example here. And we'll finish off with this one. This is example number 2. This time we want to find the tangent line. The tangent line to the curve, excuse me, x y squared plus x cubed equals 10 at the point point 1, 2. Okay, so now notice we said the tangent line to the curve. Okay, this whole, let me go back to black here for a second. This whole x dot n equals p dot n, this is true in any number of dimensions. This is the general form of the equation. So whether we're working in 3 space, 2 space, 15 space, that's the equation that we work. So like we said before, when you have a curve, you have a tangent line. When you have a surface, you have a tangent plane. Well, now let's move on to another dimension. When you have a surface in 4 space, well, you're going to have something that we call a hyperplane, but we still use the same language for 3-dimensional space. You're going to have a plane. We can't draw it out, but that's what you have. So this equation still works even though we're talking about a tangent line and a curve, as opposed to a tangent plane and a surface. It's the same equation. In other words, it's still going to be x dot the gradient of f at p is equal to p dot the gradient of f at p. And that's what's wonderful about this, is this equation is universal. And that's the whole idea. We want to generalize and abstract so that it works in any number of dimensions, not just 1 or 2. Okay, so let me go back to blue here. So what we want is, again, let me write it one more time. I know that it's a little redundant, but it's always good to write. Gradient of f at p is equal to p dot gradient of f at p. And of course, these are that way. Okay, so we're going to let x, of course, equal to xy. That's the component form. Well, our f of xy, or let's just say our f, let's leave off as many variables as we can, is x y squared plus x cubed. So let's go ahead and form the gradient. So the gradient of f is equal to, well, it's equal to the first derivative of f, the second derivative of f, and that's going to equal y squared plus 3x squared, y squared plus 3x squared. That's the partial derivative of f with respect to x. We're holding y constant, so we just treat this like a constant. That's why it's y squared plus 3x squared. And then the second derivative, which is the derivative with respect to y, in this case, this one doesn't matter. We're holding x constant, so that goes to 0. And here it becomes 2xy. That's it. Now, nice and systematic, the gradient of f evaluated at p. We go ahead and put the values of p, 1, 2, into this. So wherever we see an x, we put a 1. Wherever we see a y, we put a 2. That equals 2 squared is 4 plus 3. And then 2 times 1 times 2 is 4. So we should get 7, 4. And I hope that you're checking my arithmetic. So when we put it back into that, now that we actually have some vectors to work with, x is xy. The gradient of f at p is 7, 4. P itself is 1, 2. And the gradient of f at p is 7, 4. So there we go. Now we do the dot product. This is 7x plus 4y. 1 times 7 is 7. 2 times 4 is 8. And if I'm not mistaken, we get 7x plus 4y equals 15. There you go. Finding, in this case, this is the equation of the line that is tangent to this curve at that point. That's it. That's all that's going on. You're just using the idea that the gradient vector and the velocity vector are perpendicular. That's always going to be the case. Thank you for joining us here at Educator.com. In the next lesson, we're actually going to do more examples using the concepts that we've been studying recently, partial derivatives, tangent plane, gradient, just to make sure that we have a good technical understanding of what's going on and we develop some comfort before we actually move on to the next topic, which is going to be directional derivatives. So next time, further examples. Take care. Talk to you soon.